Hello friends, this will be a second tutorial on cutting plane algorithms. Basically, I will make an example to show you how we can sketch a Gomory cut, a cut that we generated into the feasible region. I will demonstrate this using a program with two variables so that we can represent it in the two-dimensional space. Okay, so let's get started. Let's consider this maximization problem. Okay, so we are given this maximization problem with two decision variables x1 and x2, and both of them are integers, and we have two constraints. Okay. So this is the problem that we are going to solve using the cutting plane algorithms. In this example, I want to demonstrate how we can sketch the generated cut into the graphic of this problem. Okay, that's why we have only two decision variables. Okay, in order to solve this using the branch and cut method, the first thing that we need to do is to get rid of the integrality restrictions. Okay, so we just remove this part and we assume that this is an LP. So we solve its LP relaxation. And in order to solve the LP relaxation, what we do is we convert, the first step is to convert these constraints into standard form. So in standard form, all decision variables should be greater than or equal to 0, and all constraints should be equality. If they are not equality, then by adding some slack variables, if it's less than or equal to, or if it's greater than or equal to, by subtracting excess variables, we convert them to equality. So it means that when we convert it to equality, again, we don't have this integrality restriction. We have this first constraint and second constraint. Okay, we have two slack variables, S1 and S2 are slack variables. And then we solve this problem using the simplex algorithm, and we come up with this optimal simplex tableau. Okay, so this is the optimal simplex tableau. In this tableau, don't be confused, row 0 is written below. Okay, as I said, in different books or in different sources, you may have different formats, different styles of writing this. And in this one, row 0 is written to the bottom row, but until now we were writing it at the top row. Nothing is different, everything is the same. Okay, the two constraints, we have this constraint and this constraint. The right hand side values are given, and this solution, if you look at this solution, x1 value is equal to 2.25 and x2 value from the second constraint is 3.75, and z value of this LP relaxation is 41.25. Okay, so as you can see, this is not an integer solution. It means that we need to generate some cuts and include those cuts into the model and reoptimize. Okay, let's generate the cuts corresponding to this first constraint. Okay, so first I will write the cuts as an exercise, and then I will sketch the feasible region of this problem and try to show those cuts in the feasible region. So the first constraint says basically this: 1 times x1, because of this 1 here, 1 times x1 plus x2, coefficient of x2 is 0, plus for S1 it is 2.25, and I'm just dividing it into integer plus positive fraction times S1. This is negative 0.25, so it means that I need, in order to have positive fraction, I need to write it as -1 plus 0.75, so that the summation makes -25 S2, and the right hand side, okay, so this is equal to right hand side 2 plus 0.25, and for the cut, we just delete the integers. So this is 1 times x1. We just delete the integers, okay, all integers, and change this sign to greater than or equal to. It means that 0.25 s1 plus 0.75 s2 is greater than or equal to 0.25. Okay, so this is the cut. So if you want, you can rearrange this because, for example, this 0.25, it means 1 over 4. This is 3 over 4, and this is 1 over 4. So you can just ignore those over 4s and etc. And you can basically write this as S1 plus 3S2 greater than or equal to 1. Okay, so you can convert this constraint into this version. What about the second cut? Let's consider that second cut now. Okay, so corresponding to this second constraint, the coefficient of x1 is 0 from here, and coefficient of x2 is 1, so I'm writing 1 times x2. Okay, for s1 it is minus 1.25, so in order to have positive fraction, I'm going to write minus 2 plus 0.75 s1, and for s2 it is already positive fraction, 0 plus 0.25 s2, and this sign is always greater than or equal to, and the right hand side is 3 plus 0.75. Again, delete the integer parts. Okay, sorry, initially you should write this as equality, and when you delete the integer parts, you should convert it to greater than or equal to. And then we have this constraint 0.75 s1 plus 0.25 s2 greater than or equal to 0.75. And again, you can simplify this as by just multiplying with suitable coefficients with 4 basically. You can say that 3s1 plus s2 greater than or equal to 3. Okay, so we have now these two cuts. In the following, I will sketch the feasible region of this problem and try to demonstrate this cut in the feasible region. Okay, and now if we sketch the feasible region of the problem, the first constraint is x1 plus x2 less than or equal to 6. So this is the first constraint here. Let me write x1 plus x2 less than or equal to 6. So we are taking this side of the constraint. And this is the second constraint over here, which is 5x1 plus 9x2 less than or equal to 45. And the optimal solution appears at this intersection here because we try to maximize such an objective function, and the optimal solution is here, and it's not integer, and the integer feasible region is only these black dots within this region, shaded region. Okay, now remember we generated two cuts, and you can use any one of them to include in this graph. Basically, I'm going to use randomly the second cut that we generated. And the second cut, let me remind you, 3s1 plus s2 greater than or equal to 3. Okay, so this is the cut that we generated using the second constraint. Now I'm going to sketch this cut in this graph. Remember the two important properties of a cut. The first property is the LP optimum solution should be out of the feasible region. This is the first important property. And the second important property, none of the integer solutions should be eliminated. So it means that this optimal solution should be out of the feasible region, but none of these integer solutions, these black spots here, none of them should be out of the feasible region with this cut that we are going to include. And let's try, let's see if it is the case. But there's a problem here. You see, in this feasible region, the axis is, this is x1 and this is x2 axis. But in this cut, we have S1 and S2. They are not x1 and x2. They are two different things. So how can I include this cut in this feasible region? Okay, for this purpose, you need to come to this standard form. In this standard form, I need to convert this S1 and S2 in the cut into x1 and x2. And let's concentrate on the first constraint here. What is it? It says that x1 plus x2 plus s1 equals to 6. And using this, it's an equality, it's an equation. Using this, I can say that s1 is equal to transferring s1 and x1 and x2 to the other side. I can say that s1 is equal to 6 minus x1 minus x2. And using the second equation here, second constraint, again I can write that this S2 is equal to 45 minus 5x1 minus 9x2. Okay, again this is the standard form, and in this standard form, since we have this equality, okay, I can write these S1 and S2 in this way. Now I can replace this S1 and S2 in the cut to obtain this solution. Let me write it here. 3 times S1, and for S1 I am writing 6 minus x1 minus x2, and S2, so for S2 I am writing 45 minus 5x1 minus 9x2, and the right hand side is greater than or equal to 3. Okay, so let's open this. 18 minus 3x1 minus 3x2 plus 45 minus 5x1 minus 9x2 greater than or equal to 3. Okay, then when you rearrange all the terms here, you obtain 8x1 plus 12x2 less than or equal to 60. Okay, now this equation is the same with this one. So this star and this one are exactly the same. The only difference is one of them is written with S1 and S2. The other one is written in terms of x1 and x2. And since I have x1 and x2, I can continue. I can sketch this on the feasible region, on the graph. And how do we do it? Basically, we just find the intersection points. If x1 is 0, then x2 is 60 over 12. Okay, and if x2 is 0, then x1 is equal to, if x2 is 0, x1 is equal to 60 over 8. Okay, so this makes 5 and this makes 7.5. Okay, then the new constraint passes through 7.5, which is this one, and 5, which is this one. Okay, so I will try to sketch this one. Hopefully I can sketch it in a correct way. Okay, from here it will pass through. Okay, sorry, it will pass through. Okay, I will try again. It is difficult to sketch with this one. Again, we will start from here and move like this and through this one. Okay, it will be a line like this, and we are going to select this part of this line. It's less than or equal to, and you see it passes directly on this point here, and you see this portion over here now is out of the feasible. With this cut, it's infeasible. It means that the old optimum solution, LP optimum, this one is now out of the feasible region. Together with all the solutions in this area, they are all out of the feasible region. But if you check, all the black spots, black dots are still inside the feasible region, and it means that this is a valid cut. Okay, so this is how we can sketch the generated cut in the feasible region for the two variable programming case, for a two variable example. And we generated the cut, we sketched the cut for the second cut that we generated. This is the second cut. Okay, so please, it's an exercise for you. If you remember, we generated two cuts. The first cut was this, S1 plus 3S2 greater than or equal to 1. Okay, so please sketch this cut in the feasible region and see that these two properties of the cut, these two properties are still valid. Okay, and when you are sketching this one, again you need to consider this method. Okay, this was a tutorial to show you how you can sketch the cut that you generated using the Gomory method or the fractional cut on the feasible region.